Hey everyone, and welcome to another deep dive with me and our expert here to break down some really cool science stuff.
Always happy to be here.
So today we are tackling this essay by Yurgo Schneppet called Plasmon? Innovation Stubber into Quantum Technology, which I will admit right off the bat, I needed some help with the translation on.
Yeah, it's a mouthful, but basically it means plasmas are driving innovation in quantum technology.
Okay, see, that's much clearer. But before we even get to the quantum part, I think we need to back up a bit and talk about what plasmas actually are. I mean, most people probably think of sci-fi movies and, glowing energy beams.
Yeah, that's a common misconception. Plasmas are way more than just special effects. They're actually a fundamental state of matter, just like solids, liquids, and gases.
Oh, wow. So like the same level as those. I always thought of them as something kind of separate.
No, they're right up there with the big three. But the key difference is that plasmas are made up of free-floating ions and electrons.
Okay, so instead of atoms all bound together like in a solid, you've got these charged particles just roaming free.
Exactly, and that's what gives plasmas their unique properties.
So like what kind of properties are we talking about? What makes them so special?
Well, Schnepp highlights this concept of quasi-neutrality, which might sound a bit counterintuitive.
Quasi-neutrality. That's a big word. Does it mean what I think it means?
It basically means that even though you have all these positive ions and negative electrons zipping around, the plasma as a whole maintains a pretty neutral electrical charge.
Okay, that makes sense. I guess I wouldn't want to walk by a plasma and suddenly get zapped.
No, you're safe there. It's like a delicate balancing act where the charges cancel each other out.
So it's not really the charge itself that's the big deal with plasmas then.
Right. What really sets them apart is their collective behavior.
Collective behavior. They all act together.
Exactly. Because of those long-range electromagnetic forces between the particles, a plasma can behave almost like a single entity. You get these really cool phenomena like plasma waves, where disturbances ripple through the entire plasma like a synchronized dance of ions and electrons.
So it's not just a bunch of individual particles bouncing around.
Yeah.
They're all connected through these forces.
Precisely. And that's a crucial aspect when we start talking about their role in quantum technology.
Okay, but before we go there, I'm curious where we actually encounter plasmas in the real world.
Yeah.
Outside of, science fiction.
Well, they're more common than you might think. Stars, for example, are essentially giant balls of plasma.
Oh, wow. I never thought about it that way.
And lightning, that's plasma too. Even something as everyday as a neon sign is using plasma to create that bright glow.
So we're literally surrounded by plasmas every day.
We are. And once we start looking at plasmas through the lens of quantum mechanics, things get really interesting.
Okay. You have to explain that one. What do you mean with quantum plasmas?
It's basically when we start to consider the quantum nature of the particles in a plasma.
So like the really tiny world starts to affect how the plasma behaves.
You got it. This happens in a couple of key situations. One is when the particles are so tightly packed that their wavelengths, their quantum footprints, start to overlap.
Wavelengths overlapping. I can't even picture that.
It's almost like they're bumping into each other in the quantum realm. The other situation is when the temperature gets so low and the density gets so high that the electron's unique quantum properties become super important. They start acting less like individual particles and more like a collective wave.
Okay, my brain is starting to hurt a little, but I think I'm following.
It's definitely a mind-bending concept. But the takeaway is that in these extreme conditions, like in a star or a super-cooled lab experiment, plasmas start to show their quantum side.
So how does that quantumness change how they act?
For one thing, it affects how waves travel through them. Instead of smooth, continuous waves, you get these quantized waves where the energy levels are restricted to specific values.
Like instead of a ramp, it's more like a staircase.
That's a great analogy. And it also impacts how the particles scatter off each other and even the overall stability of the plasma. You start to see effects that just wouldn't happen in a classical plasma.
So these quantum plasmas aren't just a scientific curiosity. They actually have the potential to be really useful.
Exactly. And that's where their role in quantum technology really comes into play.
Okay, I'm ready to hear more about that. But maybe after a quick break so we can all process this quantum stuff.
Sounds good to me. Welcome back. So we've covered a lot of ground talking about those strange quantum plasmas, but now let's shift gears a bit and talk about something a little more down to earth. Schnepp spends a lot of time on this idea of plasmonics.
Okay, plasmonics. That's a new one for me. Is that like electronics but with plasmas instead?
Not Not quite. It's more about how light interacts with plasmas, especially at really tiny scale.
And light and plasmas. So those neon signs we were talking about earlier.
That's one example, but plasmonics takes it way further. It's about using plasmas to manipulate light at the nanoscale, which opens up all sorts of possibilities for quantum technology.
Okay, color me intrigued. How does that even work?
It all comes down to these things called surface plasmons. Imagine a wave of electrons sloshing back and forth on the surface of a metal. That's essentially what a surface plasmon is.
Okay, I can kind of picture that.
Sure.
But how do these surface plasmons actually help us with quantum tech?
Well, the really cool thing is they can interact with light in a very specific way. They can actually squeeze light down to incredibly small scales, way smaller than what you could achieve with traditional optics.
So like tiny little antennas for light.
Exactly. And that ability to manipulate light at the nanoscale is a game changer for building things like quantum computers and communication networks.
Okay, I'm starting to see the potential here. So what are some specific examples of how plasmonics is being used?
Well, one example is something called plasmonic waveguides. These are basically like tiny optical fibers that can guide light signals along specific paths.
So we're talking about the equivalent of fiber optic cables, but at the nanoscale.
You got it. And that's essential for building optical circuits on a chip, which are crucial for quantum computers.
That sounds incredibly difficult to make.
It's definitely challenging, but the potential is huge. And it's not just about waveguides. Schneppat also talks about enhancing something called light-matter coupling.
Light-matter coupling. That sounds pretty abstract.
It's basically about how strongly light can interact with matter. And it's particularly important when we're dealing with things like quantum dots.
Okay, remind me what quantum dots are again.
They're essentially tiny semiconductors that can emit light when excited. They're kind of like artificial atoms that we can control.
So how does plasmonics come into play with quantum dots?
Well, by strategically placing plasmonic structures around these quantum dots, we can actually enhance that light-matter interaction. It's like giving the light a helping hand to interact with the quantum dot more effectively.
Interesting. So it's like the plasmons act as a bridge between the light and the quantum dot.
Exactly. And that can be used to create more efficient single-photon sources, which are essential for quantum communication.
So plasmonics can help us create those individual packets of light that are so important for quantum networks.
Yes, and it can also be used to create super-sensitive detectors that can pick up those single photons. These are called nanophotonic resonators, and they could revolutionize quantum sensing.
So we're talking about everything from miniaturized optical circuits to single photon sources and ultra-sensitive detectors, all thanks to plasmonics.
Exactly. It's a really versatile tool for manipulating light at the quantum level. And one of the most exciting aspects is its potential for solving the scaling challenges in quantum computing.
Scaling challenges. You mean building bigger and better quantum computers?
Exactly. As we try to build more complex quantum computers with more qubits, we need to be able to control light and matter at these incredibly tiny scales. And plasmonics is a really promising way to do that.
So it sounds like plasmonics is kind of like the glue that's going to hold all these different quantum technologies together.
That's a great analogy. And it doesn't stop there. Plasmonics also has a huge role to play in quantum communication.
Okay, I'm ready to hear more about that.
Yeah.
How can we use plasmonics to send quantum information?
Remember those plasmonic resonances we talked about earlier, where the frequency of light matches the natural frequency of the plasmon?
Right, it's like hitting a tuning fork and making another one vibrate at the same frequency.
Exactly. Well, those resonances turn out to be incredibly useful for manipulating quantum information. For example, we can use them to boost the efficiency of those single photon sources we talked about earlier.
So making those single photons even brighter and easier to detect.
Yes, and we can also use plasmonics to actually transmit quantum information, especially when we're dealing with entangled photons.
So we're talking about sending entangled photons across a plasmonic network.
That's the idea. It's like building a quantum internet where information can be sent instantaneously and securely.
That sounds straight out of science fiction.
It does, but the science is real.
Yeah.
And one of the most promising applications is something called quantum key distribution, which uses entangled photons to create unbreakable encryption keys.
So we could use plasmonics to build a super secure communication network that's impossible to hack.
Exactly. It's one of the most exciting prospects in the field of quantum communication.
Wow, plasmonics really does seem like a game changer for quantum tech. It's like it's opening up a whole new world of possibilities.
I completely agree. And it's not just about building devices. Schneppat also highlights the importance of using plasmas to control individual ions, which are essential for certain types of quantum computers and sensors.
Right. I remember we talked about ion traps earlier. But I always thought of plasmas as being super hot. Not exactly the best environment for delicate quantum systems.
That's a good point. But it turns out we can also create cold plasmas in the lab. And these cold plasmas can actually be used to cool down ions.
Wait, so something we think of as hot can be used to cool things down.
It might seem counterintuitive, but it works. It's like using a cold compress to reduce swelling. In this case, the cold plasma acts as a refrigerant for the ions. Schneppat mentions a couple of techniques like laser-cooled plasmas and electron-cooled plasmas.
So it's like using a super precise laser or a beam of cold electrons to gently nudge those ions into a calmer state.
Exactly. And this ability to cool down ions is really important for tackling one of the biggest challenges in quantum computing, thermal decoherence.
Right, if those qubits get too hot, they lose their quantum properties. It's like trying to write on a piece of paper that's constantly shaking.
That's a perfect analogy. So by using plasmas to cool down ions, we can create a much more stable environment for those delicate quantum operations to take place.
So plasmas really are multi-talented. They can create ions, trap them, cool them down, and even manipulate them at the nanoscale.
They are. And we're only just beginning to explore all the ways they can be used in quantum technology. Schneppat even goes into the fascinating world of using plasmas to create and control new quantum materials.
Okay, that sounds really interesting. What can you tell me about plasmas and quantum materials?
Well, you know how quantum materials have been making a lot of headlines lately? They have these amazing properties that defy classical physics, all thanks to quantum effects.
Yeah, I've heard of things like superconductivity and topological insulators, but I have no idea how we even make these materials.
That's where plasmas come in. It turns out they're incredibly useful for creating and tailoring the properties of these quantum materials. We're not just talking about finding them in nature, we're actually synthesizing them from scratch, using plasmas.
Wow, so we can actually engineer these exotic materials using plasmas.
Exactly. Schneppat mentions a few techniques. One is called plasma-enhanced chemical vapor deposition, or PCD. It's basically like using a plasma to spray paint thin films of material onto a surface.
So like a super precise way to create layers of atoms.
You got it. Another technique is plasma doping, which is all about introducing impurities into a material to change its properties. It's like adding spices to a recipe, but in this case, we're tweaking the electrical conductivity or magnetic properties of a material.
So we can use plasmas to fine-tune the properties of these quantum materials.
Exactly. And there's also something called plasma-induced nanostructuring, which is basically using plasmas to etch away material or create tiny features on a surface. Think of it like microscopic sculpting.
So plasmas can act like tiny little chisels for shaping materials at the nanoscale.
Precisely. And that's really important for creating the intricate structures we need for things like quantum processors.
It sounds like plasmas give us an incredible level of control over these materials.
They really do. And one of the most important aspects Schneppat highlights is defect control.
Defects?
Yeah.
I thought those were a bad thing.
Yeah.
Don't we want our materials to be perfect?
Well, it depends. Sometimes defects can be a nuisance, but in other cases, they can actually be really valuable. Take diamonds, for example. Certain types of defects in diamonds, called nitrogen vacancy centers, can actually emit single photons, which are incredibly useful for quantum communication.
So we're not just talking about creating perfect materials, but actually engineering specific imperfections into them.
Exactly. And plasmas are really good at controlling these defects. We can use them to introduce specific types of defects or even heal defects that are causing problems. It's like doing nanoscale surgery on a material using a plasma beam as our scalpel.
That's incredible.
Yeah.
So plasmas are essential not just for creating these quantum materials, but also for fine-tuning their properties and even controlling those tiny imperfections.
Exactly. And that level of control is really what's going to enable us to build the next generation of quantum technologies.
Okay, I'm completely blown away by all of this. Plasmas really are the unsung heroes of the quantum world. They're involved in everything from building qubits to creating new materials to controlling individual ions. It's amazing.
It is, and we've only just scratched the surface of what's possible. I think we're at the very beginning of a new era of quantum technology, and plasmas are going to play a central role.
Well, this has been an incredible journey through the world of plasmas and quantum tech. Thanks to Jorgo Schneppat for giving us so much to think about.
Absolutely. His essay really highlights the amazing potential of this field, and who knows what breakthroughs we'll see in the coming years.
I can't wait to find out. But for now, I think it's time to wrap up this deep dive.
Agreed. Thanks for having me.
Thanks for listening, everyone. We'll see you next time for another deep dive into the world of science and technology. All right, so we spent the last two parts really diving deep into plasmas and how they're shaping the future of quantum tech. thanks to this amazing essay by Yorgo Schneepat.
Yeah, I mean, it's pretty mind-blowing how these tiny particles are involved in some of the most cutting-edge areas of research.
It really is. And what I find so fascinating is that we're still just scratching the surface. Schneepat's essay gives us just a glimpse of what might be possible. But that glimpse is enough to really get the imagination going. What about you? What are you most curious about after all of this?
Honestly, the idea of using plasmas to control those superconducting qubits is what really sticks with me. It's such a clever way to merge the speed and sensitivity of plasmonics with the stability of superconductors.
It does seem like a match made in quantum heaven. Imagine the potential quantum computers that operate at lightning speed, thanks to those super fast interactions between plasmons and superconducting circuits. It could open up a whole new world of possibilities for quantum computing.
Exactly. And then there's that whole area of using plasmas to create and control those new quantum materials. Who knows what kind of breakthroughs we might see in materials science and physics.
Right. We could discover materials with completely new properties which could lead to advancements in energy storage, quantum sensing, who knows what else. It's almost like we're entering a new era of materials. Science and plasmas are leading the way.
Absolutely. And let's not forget about quantum communication. The idea of using plasmonic networks to send entangled photons across vast distances is mind-boggling. It could revolutionize how we communicate and process information in a truly secure way.
Just think unhackable financial transactions.
Yeah.
Instantaneous global communication. It could transform the world as we know it.
It really could.
So let's do a quick recap of all the amazing things we've learned about plasmas and quantum technology. We've seen how they can be used to create and control those essential building blocks of quantum computers, those qubits. We've explored how they're crucial for synthesizing and engineering those exotic quantum materials with their incredible properties. And we've even delved into how they can help us manipulate light at the nanoscale to build super fast and secure communication networks.
And don't forget that important role they play in cooling down those delicate ions, protecting them from decoherence. It's amazing how versatile these electrically charged particles can be.
It really is, and it all comes back to those unique properties we talked about earlier. Their electrical conductivity, their ability to create those collective waves and oscillations, and their sensitivity to electromagnetic fields.
All of those properties make them incredibly powerful tools for exploring and controlling the quantum world.
Well, this has been an amazing journey. Thanks to Yorgo Schneepat for giving us so much to think about in terms of plasmas and quantum technology. And thanks to you for listening. Hopefully you've enjoyed this deep dive as much as we have.